Hey everyone, welcome back. This is the next video. This is actually some material that we're supplementing into our book. It's not a section in the book. So this section is called Conditionals, Equivalent Forms, and Venn Diagrams. So we're going to start with some vocabulary terms. Statements involving and, or, and not. So first, a conjunction. A conjunction is when you put two statements together involving the word and. So this might say blah, 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 and blah, 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 blah. Right? We're combining the two statements to make one conjunction. The disjunction is when we combine two statements involving the word or. This would say blah, 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 or blah, blah, blah. We're putting the two statements together to make one disjunction. And then we have the negation. And this is a statement involving the word not. So you could think of something by saying not blah, blah, blah. Right? So let's look more closely at each one of these. A conjunction is true when both statements are true. So I show you this notation, and this notation here says P and Q, right? We have a statement that we're representing with the letter P. And then we have a second statement that we're representing with the letter Q. If we put those two statements together, connect them with the word and, we have a conjunction P and Q. Now for our conjunction, the entire statement to be true, we need both statements, individual statements, to be true. We need the statement P to be true and the statement Q to be true. This can be represented by a Venn diagram. We talked about Venn diagrams before with polygons. In our Venn diagram, we have the universal set represented by the rectangle, which would include all statements, including our statement P and our statement Q. You can see our circles for statement P and Q overlap because in order for the conjunction to be true, we need both statements to be true at the same time. Now on the Venn diagram, we represent the conjunction by the overlapping region of the two circles because it's this region on the Venn diagram where both statement P and statement Q exist at the same time. Or in other words, it's where both statements are true at the same time. Next, the disjunction. The disjunction, remember, is two statements combined with the word or. And it is true when at least one statement is true. So now I'm showing you the notation for a disjunction, P or Q. Now, in order for our disjunction to be true, we need either statement P or statement Q or both statements to be true. We can represent this with a Venn diagram. Again, we have the universal set with the rectangle and circle P and Q representing our two statements. Now, if statement P was true and statement Q was false, we would be looking at this region of the Venn diagram right here. If statement Q was true and statement P was false, we would be looking at this region of the Venn diagram. If both statements are true at the same time, we're looking at this region here. Now, in order for a disjunction to be true, either statement P can be true and Q can be false, Q can be true and P can be false, or they both can be true. So, in the Venn diagram, it's the entire region of circle P and of circle Q and the overlapping region that makes the disjunction true. Finally, we have the negation. The negation represents everything but the statement. So the notation here is not P. Looking at our Venn diagram, the part of the Venn diagram that represents the negation of P, or not P, is everything outside of circle P. So all of this and everything inside of circle Q that doesn't overlap with P. Here's an example using Venn diagrams and some different statements. We have to match the portion of the diagram with the statement it represents. So in part A, it says James is a freshman and is in the drum line. Now you can see the Venn diagram, the different regions are labeled X, Y, Z, and W. Now if James is a freshman, he must be in the freshman circle. And he is in the drum line. So he must be in the drum line circle. So of course, looking at this Venn diagram, we must be talking about the region where the two circles overlap, which would be Y. Part B. Sarah is a sophomore and is not in the drum line. You'll notice the statement in part B is both a conjunction and includes a negation. Now let's look at the Venn diagram. Since Sarah is a sophomore, she is not inside the freshman circle. And she is not in the drum line, which means she is not in the drum line circle. Therefore, the region of the Venn diagram that represents statement B is W. Part C. Christian is a sophomore and is in the drum line. So this is a conjunction because of the use of the word and to connect the two statements. Christian is a sophomore, which means he's not in the freshman circle, and he's in the drum line, which means he is in the drum line circle. So this must be region Z. And finally, Bob is a freshman and is not in the drum line. So this is a conjunction and includes a negation. Since Bob is a freshman, he's in the freshman circle. He's not in the drum line, which means he's not in the drum line circle. So we are talking about region X. Next, we're going to look at how conjunctions and disjunctions relate to a number line and inequalities. So our goal here is to graph each of the following inequalities. So in part A, it says x is greater than 6 or x is less than -1. So since we're using the word or, we know that one or the other statement could be true. So we need to graph these inequalities separately. So it says x is greater than 6. We would come over to our number line. I'd put an open circle on the 6, and greater than 6 would go to the right. X is less than -1. Here's -1, open circle on it because it doesn't equal -1. And less than -1 would go to the left. So this number line actually shows us the use of the disjunction, or, right? Because there's no number that can satisfy both inequalities at the same time. You're either going to choose a number over here that satisfies this inequality, like the number 7, or you're going to choose a number that satisfies this inequality, like the number -4. Part B, x is greater than or equal to 6, and x is less than -1. Well, let's look at graphing each of these inequalities. So greater than or equal to 6, I would now use a closed circle on 6 because it can equal 6, and greater than goes to the right. X is less than -1, that has an open circle, and less than goes to the left. This graph looks very similar to the graph in part A. However, the statement is very different because of the use of the word and. This is a conjunction. Now notice, we cannot find a value that satisfies both of these inequalities at the same time. There is no number that is both greater than or equal to 6 and less than -1. This is shown by the number line. So the statement in part B is impossible. Part C. X is greater than or equal to 3 and x is less than 8. Well, greater than or equal to 3 would be a closed circle on 3 and greater than. X being less than 8 would be an open circle on 8 and be less than 8. Now the statement in part C is a conjunction because of the use of the word and. This means that we must satisfy both inequalities at the same time. So the true graph of part C only involves the numbers that satisfy both inequalities at the same time. So we cannot use any numbers bigger than 8, and we cannot use any numbers less than 3. It's only the numbers from 3 up to 8 that satisfy both inequalities at the same time. Finally, part D. X is greater than or equal to 3, or x is less than 8. Well, greater than or equal to 3 is graphed there, and less than 8 is graphed there. Now the statement in part D is a disjunction because of the use of the word or. That means we need to satisfy one or the other inequality, or both of them at the same time. So the true graph of this statement is the entire number line, because you can choose any number on this number line and it will satisfy at least one of the statements that make up the disjunction in part D. Next, we're going to talk about the different types of the word or. There's an inclusive or and an exclusive or. Now, an inclusive or means that things can happen at the same time, meaning one thing or the other thing or both things can be true at the same time. Now, the exclusive or cannot happen at the same time, meaning one thing or the other thing is true, but not both of them at the same time. Let's look at some examples here. Which type of or is being used? Number 1, to meet graduation requirements, Joe needs to take a writing course or a literature course next semester. Well, this is certainly the inclusive or. And we know that because if Joe takes a writing course, he graduates. If Joe takes a literature course, he graduates. If Joe takes both a writing course and a literature course, he graduates. Number 2, Erin can only afford to buy her friend a birthday cake or Bath & Body Works lotion for her birthday. Well, this is certainly the exclusive or. Because Erin only has enough money to get either the birthday cake or the lotion, but not both. Now we're ready to talk about conditional statements, which are also known as implications. These statements are statements that can be written in the form of P arrow Q, which we read if P then Q. I'm sure you've heard a lot of statements like this in normal everyday talk. If blah blah blah, then blah blah blah. Right? They're called implications because you are implying that if one thing happens, then the next thing will happen. They're also called conditional statements because you are setting a condition for something to happen. If this condition is true, then this will happen. We call the if part of a conditional statement the hypothesis. We call the then part of a conditional statement the conclusion. Now, there are 4 types of equivalent forms of conditional statements. The first form is if P, then Q. We could say the exact same thing if we said P implies Q. Or every P is a Q. And finally, P only if Q. We're going to finish the lesson with some conditional examples. Let's start with this conditional statement. If an animal is a boxer, then it is a dog. In part A, we are asked, what do P and Q represent? Well, if you look at the conditional statement and break it into 2 statements, we see the first part, our hypothesis, and the second part, our conclusion. So the first statement, or the first part of this conditional, we could identify as being statement P. The second part could be statement Q. So an animal is a boxer is statement P, and it is a dog is statement Q. Now in part B, it asks us to rewrite the implication in all equivalent forms. Now we see the equivalent forms listed here. 1, 2, 3 different ways to rewrite this implication. The first equivalent form would state an animal is a boxer implies that it is a dog. The second equivalent form would state every animal that is a boxer is a dog. And finally, an animal is a boxer only if it is a dog. We recognize that all 3 of these statements, along with the original implication or conditional statement, say the exact same thing and have the exact same meaning. Finally, part C. Draw a Venn diagram for the implication. Well, this requires us to understand the relationship between dogs, boxer dogs specifically, and all other animals. In this Venn diagram, the universal set, the rectangle, represents all animals. Of course, dogs are an animal, so that we have a circle representing dogs. And boxers are a type of dog, so the entire boxer circle is inside of the dog circle. And lastly, part D. Write the converse for the implication. And is the converse true? Well, we know the converse is when we take the 2 parts of a conditional statement, an if-then statement, and we switch them. So, the converse would state, if an animal is a dog, then it is a boxer. And this clearly is not true. So that's a review of conditional statements, their equivalent forms, and Venn diagrams. Now, it's going to be very important that we focus on understanding language moving forward as we start to create geometric proofs.